Hello and welcome to this subject booster on critical mineral resources. My name's Pete Rowley and I'm Senior Lecturer in Geology at the University of West England at Bristol. So critical mineral resources are a subject basically dealing with any mineral resource that is essential to the economy and whose supply may be disrupted. These have been an issue for societies for thousands of years. On the right here is an image of the Charterhouse Iron Age and Roman lead mine. These linear features are where veins of lead-rich ore ran and then were excavated by miners. And this particular mining site was active right through, as I say, from the Iron Age all the way through to the Victorian period, and was a large reason the Romans were interested in southwest England, and this became a very fortified site. Down in the bottom left, we've got an image of Bingham Canyon mine in the USA. This is one of the largest open cast mines in the world, and just to give you a sense of scale, those little dots driving around are these very, very large dumper trucks. So this is an enormous quarry. Why are we concerned about critical minerals? What are using them for? Well, just to give you an example of something that's perhaps in your pocket at the moment, if you consider a smartphone and you start to look at all of the different mineral resources which are required to create that smartphone, we're actually dealing with a huge number of different elements, and a lot of them are not the usual irons and coppers and things that you might think of. Actually, lots of the rare earth elements and more unusual elements are required for lots of this high-tech technology. And it's not just in terms of smartphones, but actually our entire renewable energy industry is also dependent on mineral extraction. So for example, solar panels require arsenic, gallium, germanium, indium, tellurium and iron to manufacture. Wind turbines, although the main casing is often polymers and steel, the turbine within it requires very powerful magnets, and so aluminium, neodymium, dysprosium, praseodymium, iron, boron are all very, very important. And battery technology is increasingly relying on elements like cobalt, graphite, lithium and manganese. So these are just the electrical components. You've also got to consider that if you're going to build a renewable resource structure, you also need plastics. So even though we're hoping that oil and gas use as a fuel is going to reduce, it's very important to recognize that actually petrochemicals, which are byproducts or products produced from oil and gas, are also incredibly critical to our developing economy. And this isn't going to go away. So plastics, coatings, fertilizers, synthetic fibers, rubber processing, and lots of the feed-in chemicals for industrial applications all rely on the processing of oil and natural gas. So although we are seeing a reduction in oil and natural gas and hopefully eventually a move to fully renewable energy, oil and gas are still going to be required for industrial processes. It's also worth noting that oil and gas extraction is the main source we have of helium. And helium is an incredibly useful element in that we use it for supercooling of magnets. So if you ever go into hospital and have an MRI, that MRI machine is cooled by liquid helium. And helium is the only element that can get as cold as we need it to. And if we just release it to the atmosphere, it's one that very quickly escapes into space because it's so light. So medical uses, as well as particle accelerators and lots of scientific and high performance instruments, are all dependent on this source of helium. So the problem we've got is that this sustainable economy that we're aiming for and any kind of effective climate change response is also entirely dependent on the extraction of these critical minerals. The problem, or the paradox if you like, is that these minerals are by their very nature not sustainable and they're not renewable. So getting the balance right between extracting the critical minerals that we need to supply the industries that allow us to become a more sustainable population on this planet, there's a real conflict there that needs to be addressed. So to look at an example of an individual element here, we're going to take copper. So copper was one of the first metals that was ever extracted. Happens to be because the ores of copper are very strikingly blue-green. So it's a very easy thing for people to have quickly identified as being diagnostic of having this metal in that could be extracted. And it happens to be a metal that basically you can put the ore in a fire and you will generate liquid metal from it. So we've been extracting copper since about 8,000 years before Common Era, so we're talking about 10,000 years ago. And the biggest role by far in the modern use is for electronics, because copper is the second best electrical conductor we know at room temperature. The only thing that's better is silver, and silver is much harder to find, therefore much more valuable. It's also, due to this kind of application in electronics, the third most used metal on the planet, after iron and aluminium. And the kind of crux of this problem we're coming to is that we're anticipating that the demand for copper is going to exceed our known reserves of copper by about 2050. So in less than 30 years, we could be looking at running out of copper. This graph on the right is just showing you the production in millions of tons per year of copper, and as you can see, there's been a pretty exponential growth, and there's no sign of that stopping. So this is an infographic. There's a link here. You can go and look at the full high resolution version and peer over this at your heart's content. But what this is showing is the consumption of different critical minerals and elements compared to their usage, and therefore how long our known reserves are likely to last. And this radial diagram is showing a variety of different elements. So for example, up in the very top, we have copper. And what this is showing is that if the global demand stays as it is, we've got 61 years of copper left as of when this diagram was made. And if demand increases, we're looking at 38 years. If you come around to indium at the 3 o'clock position, we've got perhaps 13 years of indium left, which is a critical mineral for LCD production. All the way around to silver, down towards the 7 o'clock position, and you'll find that we've got about 30 years of silver left at current usage. So we have a number of very, very pressing issues in terms of how to address this. We can hope to recycle, and on the right hand of this image you can see the proportion of these minerals which are currently being recycled. Our lead recycling is actually very good. About 3/4 of the lead that's used for new applications is from recycled sources. Our aluminium recycling is at about 50%. Our silver is currently at 16%, and we're currently recycling about 30% of our copper. But ultimately, we do need to extract new metals. And this raises an issue of geoethics. So what can we do to increase supply without damaging the planet that we are ultimately trying to save by developing a more renewable and sustainable economy? So just as an example here, this is Solo de Uyuna, which is up in the Altiplano of Bolivia, and it's 10,000 kilometers squared of salt flat. Some of you might recognize it. It was the filming location for one of the recent Star Wars films. And this salt flat is nearly 4 kilometers up in the air. It's very, very high salt flat. And these salts contain somewhere between 50 and 70% of the world's known lithium. And lithium, as you're probably aware, is very, very widely needed for new battery technology. It also happens to be very rich in borax, sodium, potassium, and magnesium, which are also very high demand metals. So the question here is, do we go in and extract this resource, or do we leave it to protect the environment that is there? And this therefore leads to a range of quite intersectional discussions about not only the geoscience, but also the economic demand, the sociology, the philosophy. It's a very complicated area, and it's something that is becoming increasingly important and critical as we discover more reserves and work out what the impacts of the extraction or not of those resources might be. As quite a nice example in the UK, down in Cornwall, about 7 or 8 miles northeast of Plymouth, is something called the Drakelands mine. It used to be known as the Hemerdon mine. And this is thought to be the 4th largest tungsten and tin reserve in the world. Back in, I think, 2011, there were 27.9 million tonnes of proven reserves in this quarry. The issue is that this quarry is right on the edge of Dartmoor, and which is a national park, and as such, it's a fairly limited quarry. It's 800 meters long and about 400 meters wide, and it doesn't really have the capacity to expand sideways. So one of the things that was done to try and improve the extraction rate here was in 2015, a series of geotechnical tests were carried out, which were to basically analyze how strong the material that made up this quarry was. And the question was whether the slope that was being maintained at the moment, which was about 30 degrees on average, could be steepened. Because if you steepen the slope, then we managed to increase the amount of resource. And sure enough, what we managed to find was that the slopes were strong enough to take a slightly steeper slope. So our proven reserves went from 27.9 million tonnes to 35.7 million tonnes. So this idea of sustainable development, yes, that quarry had already damaged quite a large area, but that was a historic problem from over a century ago. The expansion of this mine by using ingenious methods of recognizing that you can oversteepen it enabled a huge increase in the amount of extractable metal. Now, the Hemerdon mine or the Drakelands mine is a very interesting example because it also happens to have gone through a series of openings and closures and companies going bust and being taken over. There's a couple of links here you can follow for a bit more information, but it's a very nice example or case study if you want to dig into it. And finally, just here's a list of links which might be useful in terms of infographics and information on what critical minerals are, what the specific critical minerals are for the UK and our mineral risk list, and also some information there on geoethics. If you want any more information or if you've got any questions, please do feel free to get in touch.